Let's start our session for today, and maybe try to bring you more into the discussions and on board of the. I can see that you're very keen to have a lot of questions, so we'll try to give you enough chance to have questions and discuss this. So just start with the last section. So my name is Vihar Georgiev, and I work in the University of Glasgow. And next to me is Professor Richard Safik, who works in the University of Newcastle. We'll do double act, triple act, or many acts with many people here as we've been doing now. But now we want to bring you to the story and kind of to April Hub and give you a bit chance to also give some input. So the topic of this discussion, as you can see, is called Machine Learning for CMOS Beyond CMOS Design Automation in April Plus. What I do with my students usually when I have a lecture is, what the heck is this CMOS? What is CMOS design? What do you think and what you have in mind? So what I would suggest is you have already your phones in your hands. I'll give you 2 minutes to write 2 words or 3 words, what comes to mind when you have this CMOS design. What we are going to do, we will keep these words kind of as key topics or key pointers that we try to address later. But now I think it's a good time for you to really tell me what you think before we start this discussion. What means CMOS, or what is AI for CMOS? Maybe I can just explain. Do you know what is CMOS? How many people knows what CMOS? Wow, okay, we're doing better than my students, which is great. Okay, you have 2 minutes, and I will come back and I'll explain what you're going to do. I'll go and get water and I'll be back. GAA? What is GAA? Gate all around?
Gate all around,
okay. Yeah. Maybe something else, but this is what it is. Okay, we can talk about this later. Unbelievable. Very well. No electron flow. That's interesting. So we can have different physics. Spintronics, dessert. Someone wants dessert? Or I'm reading different thing on the top.
What is Santosh?
Okay, so 3 participants are typing, so I'll let 4 are typing. Oh, okay, we'll give you a couple, like 30 seconds, and we'll try to finish on time. 1 participant is typing, and okay, it's getting random number generator now. Okay, I'll count from 10 down. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Active pool. Well done to all of us. Okay, so I hope this is not going to disappear when I go further. Someone can confirm, hopefully. And we have a lot of words here, which is TCMC also. Okay, do you have shares in TCMC? Maybe some of this. Okay, it's a company and so on and so on. So the idea is that we'll pick up this later, and we'll have in the end of the session, we're going to have we call it open for discussions, and we can use these keywords here as a pointer, and I will leave you guys opportunity to use the microphone and really ask questions and have an open for discussion. Everyone gets involved. Is this okay? Good as a plan? Okay, so these are the usual suspects in this part of the team, or in this part of the April Hub. As you can see, Joydeep, Santosh, Pratibha, Richard, and me are the team and so-called researchers, but also we are supported by very brilliant people, which are here our Google-Deepmind interns, that will also give a presentation later, and we'll go very similar format like we did so far with the researchers, with the interns. And after this, we'll also have the seed funding. As you can see here at the moment, we have more seed funding, but for the first part, we will have University of Sunderland and Durham University as a seed funding, and they will come also and present their work. Also, I don't know if you're aware or not, but the seed funding was 2 rounds, 1 round and 2nd round, and the people that you see here are the funded projects for the 2nd round. I hope we will have more rounds, and also the people here from the companies or everyone else, I will encourage you guys to keep a track on these seed funding opportunities and get involved with us, which is, well, I think is a great opportunity. So these 2 seed funding which you can see here are for the second round, and there are people just starting working on these projects, or they will start working very soon. So when you come in a year time, you'll see what these people did. But now you'll see this seed funding in this case. After this, we will have April Plus, which is a new initiative or kind of different, slightly different flavor of initiative, and we'll have people explaining what it is. And now I'll reach the stage to Richard to tell you what about this pillar or this topic.
Thank you, Viha, and good evening. Rishad Shafiq from Newcastle University. It's late in the day, so also we have had a good number of technical discussions. So what we want to do is that, again, just look back into some of the things that have gone really well in the past and then put our motivation in context. So if you want to inspire the beyond CMOS research, an interesting thing to look at is the history of the CMOS in the last 63 years. Starting from the single transistor modeling all the way to billions and billions of transistors being modeled. We've hit so many laws, right? Scaling laws, Moore's law, scaling law, Dennard laws, power density laws, different types of laws. Some of them had been hit and they have died out. But still, CMOS is thriving and still going strong. On the other hand, there is a very strong community, burgeoning over time, the post-CMOS community. But due to various sort of ecosystem support or lack of it, the community is not seeing their technologies being mainstream yet, or maybe at least partly true for many of the emerging technologies. So now the question is, how can April or the Pillar 5 help designing or automating some of the processes, learning from the history of the CMOS and potentially replicating that. We will have a discussion towards the end, panel discussion, to talk about the challenges and opportunities for post-CMOS technologies. I would strongly invite you and happily invite you to join the discussions and hopefully you will participate. Some interesting facts. Obviously, software came in the 1980s. Computers became available to us, and then it became more and more available. With computing becoming more and more pervasive, we have now access to EDA tools. But a fact that has remained is that the design complexity of the type of silicon that we have today is significantly larger than some of the EDA tools can take. So much so that sometimes you have to wish for many, many months and of simulation time to basically get through the complexity. And you also need a big pocket to be able to simulate something or fabricate something. And typically, the hardware-software conundrum is also there. You design a hardware, but there's no adoption because the software is slow. And therefore, the post-fabrication design, automation, or validation, verification also falls back in the process. The fascinating thing that has happened, which we want to get inspired by, is the fact that over the so many years of design automation and also the fabrication data, reproducibility, we have been able to reduce the power transistor costs to a level which is now almost in everyone's pocket in so many millions of or billions of transistors. So something to learn from. Can we do the same thing, replicate or learn from that into the beyond CMOS research? It's a very high-level kind of slide to just talk through what we envisage that we will be doing. Digital twin is a very, to me, it's a very vague term. The way I would like to put it is that if you're designing a post-CMOS circuit or CMOS circuit, I would like to know if it works in the first place. I would like to know if it has certain electrical parameters that I should be concerned about, so that I know that there are certain electrical parameters that need to be adhered to when it comes to resilient designs or robust designs. For example, process variation was a threat for CMOS, and it still is. If you have that kind of threat for another sort of technology, how can we model it accurately so that we can cater for that kind of requirement going into the the systems level modeling? So quite often, when you, I'm sure you have already seen generative models, you have seen individual device as well as from the device to scale up into the circuits. The complexity we are talking about is quite large. And when you go from all the way from materials to devices, devices to circuits, circuits to even systems, you're looking at a really complex system. The system will most likely have a combination of homogeneous as well as heterogeneous components. Possibly in the form of something in the form of, let's say, graph neural network with a lot of these nets individually representing component level behavior and models. And that becomes really complex. The type of thing that we want to do, and we have already, you'll see that with the likes of Joydeep and Santosh, you'll see that there are some initial works going in the effort of being able to model the behavior, functional behavior, parametric behavior at device level, as well as at the circuit level. Santosh will come hopefully after Joydeep to talk about some of the device and circuit level behaviors as well. We want to model them. We want to understand if they work, what sort of electrical parameters do they offer, what is the lifetime reliability of these devices, so that we can design and fabricate with confidence. Key challenges, as the model complexity goes higher and higher, and of course, with a model like this, where you will expect that there will be semantically related and hierarchical models being more and more complex, quite often the automation efficiency is lost at the interfaces. For example, a component 1 interacting with component 2, the kind of information that they pass through the extensive data that we'll throw into the machine learning model will be only so accurate depending on the amount of data that we are throwing into it. What if there are unknown circumstances or unknown scenarios we have not catered for? So the interfaces, being able to understand hierarchical and complex machine learning models with strong interfaces, functionally verified and validated, is really, really important. And one of the other bit of a nuance going on with machine learning right now is that everybody has access to machine learning, but a lot of these machine learning methods tend to be black box in nature. I'm really pleased to see that there are some efforts around, white boxing or unboxing the complexity, which is really great. The danger of doing black box based design model is that you will never know. You'll go back to the square one when it comes to verification and validation. How can you guarantee that a requirement that you had at an input level matches the requirements that you have at the customer or someone who's using it? They have the exact same specifications that you originally designed for. So those kinds of guarantees will be very, very hard because you have a lot of ways of designing the same thing. So it will be nice to actually being able to use white box models or potentially interpretable models where you can actually explain that, okay, we came to this conclusion or we came to this set of outputs because we saw that those patterns of data. Okay. And of course, we talked about uncontrolled complexity. A common problem that we will probably discuss with the likes of April Plus as well is that, again, it's a great initiative, April Plus. The idea is that since we saw a thoroughgoing problem of lack of data, why don't we create our own circuits by ourselves and then create some circuits that can help us generating real data. So I believe that's all from me, but before I go, I want to introduce Joydeep and Santosh. Can you just raise your hands, guys? Yep. We have these two really high caliber researchers. I'm really proud that you guys are working hard. I would like to invite Joydeep now to present his research. Joydeep.
So thank you, Rishad, for introducing me. So good evening, everyone. So as you have already seen, our topic will be CMOS, beyond CMOS, this kind of thing. So both device and circuits we try to cover. Circuit, I would say circuit of few devices, but I'm not gonna go for high intensity circuits, but mainly focuses will be on devices. Devices mean a lot of things. Devices, transport modeling, and all those things, reliability issues. There are many things those are hidden in the devices. So device term, includes a lot of things. Device design, then inverse design. There have been, some of our speakers were mentioning about this earlier. Material design and inverse design. Same thing holds for device design and inverse design as well, circuit as well. So there are many things to concern. Is our concern. So I'll be talking about low power devices. Obviously, there will scope for high power devices. I haven't investigated that, but that's in my mind. So CMOS devices, low power, ultra scaled silicon based devices, that's our consideration. So yeah, we consider on silicon, new materials. We haven't investigated much, but that's also in our mind, so in our plan. And then maybe small circuits like SRAM cell, NAND, NOR logic, something like that, which uses maximum 10 transistors. We can investigate the behavior of the small circuits as well. As we know, these are kind of building block for modern logic, memory, and sensor systems. So this is a very interesting topic. So my name is Joydeep Ghosh. I'm studying this CMOS devices and circuits. Some questions related to AI. The question is, why should I introduce AI? AI is doing wonders these days. So obviously, when you think about device design, the question will be, machine learning can expedite device design method or not? First thing. And then machine learning can optimize their performance. That's another thing. Then machine learning optimize lengthy fabrication process. This is another, it's a huge topic. So process design, process modeling that I haven't investigated much. We'll be doing in later because I don't find too many literature on that. So process means if you talk about any fabrication data, that we have lots of data, right? In order to do design and reverse design on those domains is really challenging. And optimization, that's going to be really challenging. Another question is, machine learning build fast compact models. There is no compact model, so any FinFET has a compact model. Let's say BCM model, which is very famous, and then gallium nitride is a compact model, ASM, some stuff like that. So industries work on parameter extraction. So can AI expedite those things? So there are many things which should be investigated right now, which we are trying to do in April. The challenges, as you know, how to maximize performance, right? Many materials, so many parameters. In let's say FinFET, we have 10 parameters anyway, geometric parameters and doping parameters and many other things, process induced and stuff like that. If you go into process, as I told you, so there will be more parameters. So process induced variability, another thing. So variability is a huge subject, like NBTI, HCI, these kind of things. That AI has not been explored those subjects, which is itself a big topic. People can do that. Fabrication time and cost, as you can see, fabricating these devices is a Herculean task. It's not easy. Let's say 22 nanometer node, 14 nanometer node. We still, not many people have this opportunity. Industries have that, very strong industries, TSMC, those kind of things. But, it's difficult to reach to their data, right? So whatever happens in industry, that's generally stays in industry. So these are the things. One reliable thing is TCAD simulation that people have been doing. Ankit also mentioned, and a couple of other guys, SPAD design, SPAD devices, stuff like they have mentioned about TCAD simulation. This is a way out. What you can do, do TCAD simulation and calibrate with real data. Real data will be challenging to get. Real data means a lot of things. Let's say DC analysis, AC analysis, RF data, all data you cannot really get. You can only get few amount of data. You can calibrate with those data, but that's just the first step, but there are other steps as well. So traditional method will be try, simulate, repeat, blah, blah, blah. This is really optimizing. But one TCAD, by the way, one TCAD simulation takes 2 hours. That's a lengthy process. So if you do 100 simulation, 100 into 2 hours, then if you see 1,000 simulation, you'll be losing months of time. So obviously AI is required in those cases if we can expedite. So both all these things, design, how a FinFET should be designed fast, that may be a question. Optimize, quickly find best device parameters for a certain application in a particular technology node as well. These are the questions that one can solve. I'm trying to investigate these kind of things. Discover new design, new automation tool. So multi-directional integration. Yeah, obviously TCAD with Python should be, we should have to mix up these two things. Industry, as I mentioned, DC, AC transient simulations and integrate TCAD in Python. Let's say we are trying to do some optimization problem. So TCAD in Python, we'll write some code like genetic algorithm, very basic thing. Then maybe some optimization. There are a lot of optimization algorithms. I'm not going to that. And then reinforcement learning, introduce reinforcement learning for optimization. Then things. So you develop a code in TCAD and you have to run it. Develop a code in Python and you have to run it according to TCAD. So you need a kind of interaction between these two things. So there are many tools, software tools can be developed, which is what we're trying to do. So yeah, in this work, new tool under development, that's for sure. Help AI workflow and solve design optimization problem. That's my target. Inside CMOS devices, a little bit of, let's say, SRAM bit cell, but later on big circuits as well, but it will be challenging. So thanks for your patience, and then I'd like to introduce Santosh, who is beyond CMOS. He will be talking more about his new investigations. Welcome, Santosh.
London. In a quiet post-afternoon session, let's talk things differently. Trust me, when I say different, it's different. We have been using phones for quite a long time, and we know that there are some problems associated with the mobile phones. What they say is, there has been a wild ad that you use your Redmi phones to iron your shirts due to the heat. So what if we can think of technologies which uses no electron flow, basically which can harness the spins of it, the directions of it, to communicate, to process informations. We are talking about a magnetic spins, which is part of a Spintronics technology, which categorizes under beyond CMOS, as this is leading edge technologies. In that Spintronics, we have been focusing on Skyrmions, which I will introduce in a short while, how it is, what it is. So this is a next generation technology where we are thinking that it would be in a mainstream which can do conventional information processing in a more energy efficient and compact way. As in line with the April AI Hub, what are the deliverables we have developed and delivered from the modeling side? We have curated a perspective article which cuts across the edges in talking about AI-driven, how it differs from the devices, circuits, and the entire systems in line with modeling, which has been part of the frontiers in nanotechnology as a perspective article. And how are these connected to Skyrmions? As my famous slide goes here, it spins in two opposite directions like this to communicate. So as I have been involved with salsa, so I used that to see how this can be used to tell what Spintronics spins are about. And let us introduce our main hero, Skyrmion, which is a magnetic whirlpool, which is kind of rotates and detects from its absence and presence. We can understand that logic 0 and 1. We are trying to build digital logic using a non-conventional technology, which is magnetics technology. So we will be talking more about this from the circuit perspective, systems perspective, and devices perspective from our interns. You will hear from them. Let's say I am a responsible driver. I have my family behind it. I drive a car. I want my car to be driving throughout on a straight line and reach my destination. I don't want my car to bombard here on any roads, as I am a responsible driver. The same goes with the reliability, what you wanted to study. We are using artificial intelligence and machine learning models to study the reliability of the Skyrmion-based devices. As it has many applications in the computing technologies, which is an in-memory computing as well. How AI has its role to play in this? What are the streams which can help it? Are Skyrmions enabling AI devices, like for the AI hardwares, accelerators, or AI is powering the Skyrmion devices? That is an interesting feature article which has been recently published in IEEE CAS magazine from us. We have been covering the entire spectrum of Skyrmion for AI, as well as how AI-driven technologies can also steer the development of Skyrmion-based technologies to the mainstream technology. So in a traditional way, if you do it, it will take a lot of process to get your simulations done, let's say Micromagnetic simulations. But now we have our AI to the rescue. So it will predict for you, it will optimize, and it will also discover new things. But we are not only stopping there. Whatever discovered has to again validated through the entire process using the Micromagnetic simulations, so that we know that we are not getting any junk data. But what we are getting is trustworthy, explainable models from the designs. We know that Micromagnetic simulation tools exist. So other deliverable as part of modeling, what we are trying to deliver is an add-on tools, which will go with the commercial tools, let's say like the EDA tools, as well as the Micromagnetic simulation tools, whatever exists, open source like MuMax, WOOMF. We are trying to develop an add-on tool which will also include more complex features. Like say we have now AI-enabled workflows which will discover materials for us, devices for us, circuits for us for Skyrmion-based technologies. We have built a tool which is going to validate these designs, which is not possible using the traditional tools. And this workflow is going to be repeated. We discover, we validate, we predict, and then we analyze. So we are completing an end-to-end workflow and to make this tool, make this product available in the mainstream. With this, keep thinking how this is going to stream circuits, devices, and the system. You will hear more about from our interns upcoming. So before that, me and Joydeep will take some questions on this.
Okay, thank you. So maybe start with Joydeep. How you're validating your models against real data, Joydeep?
It's a very good question. Yeah, for sure. For AI model, if we build some AI models, so we need validation, right? Because we have many more AI models as well. So, for example, you can use DNNs or you can use very traditional AI or machine learning models. So you never know, and all the algorithms are working differently. So you never know what answer, whether is it correct or not. Even after showing accuracy percentage, is not sufficient. So you have to validate with real data. Real data is tough to get. So the question how to validate? Okay, so for real data validation, I look for fabrication data which are published in let's say IEDM journals or IEDM conferences or VLSI. There's at times industries do publish on those conferences, very specific conferences. So I look for real data to validate my results with there, because unless until otherwise, there's the value, right? The AI, I can publish only AI, but that's not sufficient. Thank you.
Thank you. So Santosh, for you, maybe where do you think Skyrmion technology is now, and what think AI will help you?
Perfect. As we are thinking about its mainstream technology, Skyrmion is not new to the UK community, as the government has already invested 3 major projects in Skyrmions in the past few years, and there is an active community which has been trying to develop all the fundamental physics-based mechanisms and from the physicist side. And as part of April, now we are trying to make it an engineering perspective and also add AI into the design. AI comes as an augment to this. So with this, I believe that it is going to be very soon in the mainstream technology. And we are also having our in-house fabrication team. They are trying to recreate models which we predict using our simulations and give them the values. Rather than doing 10 traditional repeats, now they can do it in 2 or 3 times. So this is going to save a lot of money and cost to the time to market and cost. So I think with this, where we are going with the April, I believe this is going to be a mainstream technology soon.
Okay, thank you. And one last question for both of you, I guess. Joydeep, how do you plan to make the database, and do you plan to make it available?
Yeah, it's a good question. So yeah, obviously, as we mentioned last time, so in materials, we have a lot of database, but in devices, we don't have. And devices are very specific, right? FinFET and GA-FET, or for example, silicon carbide, silicon, and then gallium nitride database cannot be same. So the point is we have to create our own database. There is another way. We don't have fab data that much, so we have to rely on TCAD or any other simulation tool which is reliable and which is industry standard. And yes, I'm creating a database. I would like to make it available online later on from April, so that other people can make use of it, and if they want to do something, they can. And the database, some results I'll try to verify with some real fab data, as I mentioned to you. That's my plan. Thanks for asking this.
Thank you. And Santosh, just to finish, how do you create Skyrmions? Let's be a bit more practical, and I will leave the last question for the panel session.
Yeah, that's very interesting. As we are talking about something which is not existent. This is actually not something which we can feel as a physical entity. Skyrmions are created using magnetic spins, as I have explained, using a magnetic volts. These are generated using MTJs, which my intern will talk about briefly, how this is generated using magnetic tunnel junctions, which is going to convert the electrical voltage to the magnetism, which in turn will align the spins, which is already by default available in your magnetic materials to form a whirlpool structure. And thus Skyrmion is created. And in simulation, it's just easy. You code a Skyrmion. But we are concerned about practicalities. How do you do it? That's why the next the platform is set, and we will introduce them at that point. Thank you.
Great. Let's take both of them and we'll bring them again. And now we'll move further in the interest of time. And this question, we'll take it during the panel session. So compact models, how can be replaced basically with AI? Okay, Santosh.
Thank you. So as I have been talking about the three mainstreams which they are going to introduce, how Skyrmions can be part of the mainstream technologies. First, I invite Anu to talk about the complete system perspective. Then Sarah will talk about the circuits and systems, which will precisely answer how to generate Skyrmions, how to read the Skyrmions out. And then she will end up with a device level. So this is kind of top-down and bottom-up combined. And I welcome Anu to be on stage now.
Good evening, everyone. I regard it as a special pleasure to be here before all of you to present my work as a Google-Deepmind research internship, my work that I did on the internship. So I worked on generating a large data set of Skyrmion simulations and then using machine learning to analyze that data set. Spintronics is important. The theme of this session is beyond CMOS, and what that means is that we are looking for ways to integrate Spintronics in a way that we typically see CMOS. So we know electricity, you move charge from one part of a wire to the other part. We want to do the same with Skyrmions. However, as Santosh said, that's a way more difficult problem. This is because you need to drive the Skyrmions in a straight line without it hitting either side of the border. The issue with this is that there's so many parameters that influence the trajectory of these Skyrmions, so researchers need to know which parameters are the most important in order to keep the Skyrmion in the correct track. So to do this, we use AI. So I use these 3 steps to generate a large data set, so that researchers in the future can use my data set to research what the most important parameters are. So firstly, I use the MeMax simulator Santosh introduced is a platform where you can run micromagnetic simulations. To do this, I sweeped a bunch of different parameters that are important to Skyrmion trajectories. This was a very difficult problem because there are so many, and I can't sweep all of them because that's going to be billions of simulations. So it's important to know which ones, at least at the beginning, I can focus on. I then created a script which generates maybe thousands of simulations or potential situations that the Skyrmion can be in. And then I moved that onto the simulation section, which is where I actually simulated these scripts on the MeMax 3 platform. Again, the MeMax 3 platform is a micromagnetic simulator, meaning that simulations can take hours to complete. So to fix this, I used GPU clusters and parallelization to run a bunch of simulations in parallel. As you can see at the bottom, there's an application that I had to build to classify whether these simulations were successful or not. A successful simulation is when a Skyrmion moved from one side of a strip to the other side in a straight line. And the issue is that I had to trade off accuracy for speed of the simulation. So I needed the simulations to go quickly rather than taking hours per simulation. So that meant that I can't really trust the positional information I got from the simulations for the classification. So I had to build a tool to directly classify each simulation by human interface. Then I move on to the analysis side. This is where I can actually use machine learning tools to analyze what the simulation has said. This is where I used clustering algorithms such as k-means to cluster each class. So we have an annihilation class, a successful class, a class that says that the Skyrmion moved, but it wasn't in a straight line. So all of these are relevant classes which can inform parameter information. So then once I've clustered them, I can extract features that are most relevant to moving the Skyrmion in a straight line. And what's beautiful about this is that I can flip this whole structure on its head, where I can use the analysis section to inform the simulation and generation section. So then once the models have learned what is necessary, what is good, I can then use machine learning techniques to then inform what the next simulations can be for good simulations. So thank you very much for your time.
Thanks, Anu. Now I invite Sarah to present her work.
So good afternoon, everyone. My name is Sarah, and today we'll be focusing on my research, which is called Beyond CMOS, where we're using TCAD modeling for circuit optimization and system design, system deployment. Sorry. So if you have a quick look at the slide there, you'll see a simulation happening right now. So what you see there is right now a Y device, but that is a MTJ plus a Skyrmion logic device. That are the two fundamentals that we'll be focusing on today. MTJs, also known as magnetic tunnel junctions, are the next generation non-volatile memory because of its qualities such as fast processing and quick switching speed. Why we're using, and with that we're also integrating Skyrmions. Skyrmions are essentially topologically protected. They have really good advantages, such as they're ultra small, which means they're very nanometer size. They're very quick to move. Very stable, and essentially, when they move across from one position to another, it does not require that much of energy. So if you take a quick look at the simulation, there are three different processes, which is the write, the tunnel barrier, and the read. So like Santosh mentioned, I'll explain how does the Skyrmion get generated. The Skyrmions get generated in the write process using an MTJ. There are spin currents that are injected into the MTJ, which nucleates the Skyrmion in the write process. The Skyrmions in this diagram right here represent the bit carriers. In this sense, you can think of it as like, oh, they're encoding information as they move along the way. The read process is basically where the MTJ is reading the presence of a Skyrmion based off a logic device. And if you can see in this example, this is a process of an AND gate. So overall, this is the frame, and this model was implemented into a simulator called Spectrum in Cadence, and using Verilog A modeling language. Overall, this is one of the most post CMOS processes that I was trying to uncover, and hopefully continue to work on it more.
Thanks, Sarah. And may I invite now Chi to present his work.
Thank you. My project during the internship in last summer is using machine learning to accelerate the micromagnetic simulation for Spintronics devices. So basically for Skyrmion, which is type of like magnetic texture, which is topology protected, which means it can be driven by current and other external field without damaging itself. So with this characteristic, we can use Skyrmion to develop like more beyond CMOS devices, which has like lower power consumption compared to the traditional semiconductors one. However, there's a problem here is that when the traditional way to study the dynamic behavior of the Skyrmion is that we normally use like software like COMSOL to do the simulation, which can cost a lot of time due to the complex computation for the heavily dense models and structures. So what I did here is to use a machine learning model to classify the Skyrmion behavior and to predict their Skyrmion behavior within like a few seconds. So on the left, there's a pipeline of the machine learning models. So basically, I use COMSOL to do the simulations and extract all of the data from the simulations. And I use feature extraction and machine learning model classifiers to classify the output. And so basically it can output whether the Skyrmion is moving in a straight line or whether it turns around and goes annihilation at the end. We found that the gradient boosting method is can achieve the highest accuracy, nearly 100% for 1,000 samples. Yeah, that's it. Thank you.
Thanks, Chi. And in lieu of time, we will take quick questions, and please keep your answers very short. First, we'll start with Anu. So what do you think are the methods of analysis and the future directions?
This is a really good question, and I think it informs the entirety of the project, essentially. So other methods of analysis, we could use, I've been investigating using CNN, so analyzing the animations that we get from the simulation results in order to automate the classification process. Then there's the just feature extraction models and other regression models as well, just to get as much information and simplify the data set as much as possible from what we get from the simulations. And the future directions, researchers are going to be able to use this data set that I've provided for their further research, so they can do the physical work and then also use the simulations to infer results together, so they can have more of an accurate approach to Skyrmion research. Thank you.
Thanks, Anu. For Shara, what is the PCMA used in your circuit diagram? If you can explain that in a short, please.
Okay, so you guys have heard of a multiplexer, correct? So a VCMA is, in that sense, works that way. So in the sense that we are switching between two different logic gates, such as AND gate and OR gate. So if the VCMA has an inputted voltage of 1, essentially that's operating as an AND gate, because that acts as a very strong barrier for the Skyrmions for both the Skyrmions to be able to pass through. Imagine if just one, if you think about it as like a normal truth table, if there are two ones, it acts as a 1 input for the AND gate. However, if it's just 1 and 0, but the operation acts as a logic gate for the AND gate, it does not pass through at all. But if it's a 0, it acts as an OR gate, because the barrier is weak for it to be able to pass, for both one or two Skyrmions for it to pass through. Yeah, thank you.
Thanks, Sarah. And Chi, what is the limitation of your current model, do you think?
I think the current, the data size of our data set is quite small, because we are just trying to did a validation work to prove the concept that machine learning models can actually accelerate the micromagnetic simulations. So I think in the future, the data sets can be expanded to say 10,000 to learn more comprehensive information from that. Yeah.
Thank you. Thanks. It was a good answer. And due to leave of time, we are skipping that non-technical questions. You can catch them to ask what is their favorite part and what did they learn from this. Okay, thank you. And with this, let us move on to the next session. I invite Joydeep to take the stage.
So yeah, you have heard about our interns. Now it's a time to introduce our seed funding awardees. We have, as we have already shown you, we have 4 awardees. Now we have 2 who will be talking right now. So first topic is EPITONIC, enhancing performance, energy, efficiency of Tsetlin machines through non-volatile computing by Shonok Chakraborty, who is a lecturer. And then we'll be talking about improving anomaly detection in microscopic images of integrated circuits with deep learning technologies, which will be talked by Professor Huang. So can I introduce Shonok to say something about his project? Thank you, please.
Thanks, Joydeep, for the nice introduction. So my project is about enhancing performance and energy efficiency of Tsetlin machines through non-volatile computing. So just one slide. So this is the very initial part of the project. The project initiated in July this year. And I'm really thankful to April Hub for providing seed funding for that. And the primary objective of this initial part of the work is to model STD-RAM in terms of temperature. That is actually thermal modeling of the STD-RAM or magnetic RAM-based cache memories. And the short form of this name is actually THEMS. That's the acronym. And objective is to develop a comprehensive thermal model for the STD-RAM-based caches, where we have started initiating with the modeling transient and steady-state temperature of the underlying STD-RAM-based circuitry at a certain granularity level. So let's talk about the granularity of the cache memory. So when you're going to store some data, it's actually in a form of 0 or 1, which is actually called as binary digit or bit. So that bit level, we are actually trying to track the thermal properties. So how when you're going to changing from a parallel to anti-parallel or vice versa, so what are the thermal implications? So how it basically behaves in terms of temperature. And if we can change the temperature, so what are the possible implications, like several topics like thermal stability is the very first thing that frame the stems for the entire stuffs. And like when you have the change in thermal stability, that can actually change many of the other characteristics like retention time. You can have the right endurance. You can have the right cost in terms of latency, or maybe read disturbance error. So moving from bit, we have the bytes level. So once we have modeled all those things at the bit level, we'll next go to the byte levels, that is 8 bits. And followed by that, we'll have actually the cache line or blocks, so which we have started with the 64-byte cache lines or blocks. So now we are at the cache line of blocks level, then next level will be the sub-array level. So sub-array levels means we are considering 2 KB to 4 KB size of the cache memory, so that for that particular sub-array level, so how these things actually changes, so when you're making the entire cache memory. So nowadays we are going to use some, if you just consider the last level cache, we can use actually 2 to 4 MB or even sometimes 64 or 32 MB of cache. So making the thermal precision level or thermal characteristics at the some sub-array levels of 2 KB or 4 KB. So we can actually have multiple such granularity in a large LLC or large cache. So based upon that, we have actually chosen it so that because these architectural simulations are quite expensive, sometimes it takes week or sometimes more than that, 10 or 12 days. So that we have actually modeled it in some kind of, we need to actually do some kind of trade-off analysis between the size of the sub-array and the accuracy, okay? So higher the size of the sub-array, we are going to compromise the accuracy, which is not our motto of doing this kind of work. On the other hand, if we are going towards the very deeper level, smaller sub-array, then actually it will take much more time, a lot more time for the simulation. So we need to do some trade-off analysis, which is currently going on. Along with that, we are also going the read versus write power analysis, followed by that some other parameters, as I mentioned earlier. Okay, so expensive simulation at the architectural level, we started with a GEM5, which is basically a full system simulator, so that can simulate the cache memory all the way from the processor. And GEM5 will generate some kind of performance monitoring counters data that will be fed to the power model of the non-volatile SIM or NVSIM simulator, from where we can actually generate the area as well, through which we can prepare the floor plan by using some other embedded simulator called hot floor plan. And we have customized the hotspot simulator to generate the thermal traces. And finally, we're going to generate some of the time series data. That is actually the next part of the work. So where PMC values, then followed by power values, including MacPet simulator as well for the full system simulation in terms of power and area. And finally, once the temperature values are generated by hotspot, then we'll actually figure it out how we can actually reduce the entire simulation time by incorporate some of the machine learning models. So Tsetlin machine is one of them. Also, as it is time series data, we can use some LSTM model or any other machine learning model to bypass the costly simulation process. So if you want to know more about this project, so feel free to have some discussion on that. Okay, thank you, everyone.
Yeah, thanks, Shonok, with his wonderful presentation of what he's doing, who is planning to do. Then I take this opportunity to introduce or welcome Ms. Professor Huang, who will be talking about this anomaly detections in microscopic images, what he has in his mind. Can I please, yeah, welcome. Sir.
Okay, thank you, Joseph. Okay. Hello, everyone. My name is Qiang Huang. I'm from University of Sunderland. So by now, in the morning and the afternoon sessions, and I have seen many interesting work. Especially, I can find deep neural networks have been widely used in wonderful works. And so what I want to say, actually, I believe GPU cards should play important roles in these works. However, we know currently the GPU cards is very expensive, right? Certainly, there should be many reasons. One of the reasons, I think, could be the quality rate. So in order to improve the quality rate, we think the anomaly detection could be one of the important techniques. Yeah, so in order to improve the quality rate, generally we can use some techniques to analyze the scan data. So because we know in order to generate integrated circuits, so the silicon viewers will be used. So by using the the silicon wafers, so we try to get the scanning images by using the scanning electron microscopy. So this means that we can find the details from when the chip sites are produced. So we believe and using the anomaly detection, the techniques can ensure the quality, reliability, and the performance of semiconductor production. So actually, you also can find some of the examples in the top right corners, and you can find some of the normal and abnormal the images obtained by using the scanning electron microscopy. So in order to using the anomaly detection technologies, we try to also use the deep learning, neural networks-based deep learning technologies. So this means that we hope to improve not only the effectiveness of the performance, but also the efficiency and the robustness when we use deep neural networks. So currently, in our initial experiments, we are using the shallow deep neural network, for example, like the resolution night. So I believe and has been widely used in some works here. So it's the reason I have side explained. So we hope not only to improve effectiveness, but also want to improve the efficiency and robustness. But in the next stage, we hope to develop some of the advanced deep neural architectures, so which can not only used in our work, but also can be used in other part of this April AI Hub. So this, okay. Okay, so this is just samples that you can find these samples, normal and abnormal things. So we also did some initial experiments and shows the good classification things, and also show some currently unsuccessful classification samples. Yeah, it's currently and what we are doing.
So thank you, both of them. They have been very, they showed you all the results and some of the things. I don't have much time, so may I ask a couple of questions? Maybe we have time for one or two questions. For Shonok, how temperature impacts the STT RAM? Can you please tell us?
Yeah, so at high temperature, basically their circuit delay increases, and that actually impacts the write performance mostly, so which we are worrying about for the STT RAM. So write cost in terms of both latency as well as for write power, write energy actually increases, and apart from that, their retention time basically drops, because retention time has a strong dependency on thermal stability that further depends on the current temperature of the circuit. So higher the temperature, lower the stability, and actually that will actually degrades the write operations, okay? And I think that regarding Thames project, okay, how do you validate? Okay, so currently we are doing some kind of prototype model in terms of theory for the how we can, so when we have some flipping in bit or any change in bit, so we are now developing thermal model for that in theory. And once that is done, then we are going to implement it in some very fundamentally C or C++ language that will actually makes the simulation process very much faster. And then this will be implemented in the simulator like GEM5, which is widely accepted by the computer architecture community across the world through academia and industry. And then by using some kind of benchmarking applications from different genres like graph, hypergraph, graph theoretical model, or maybe from something from the visualization and computer graphics, multimedia, social networking, those applications will be used to benchmarking the entire things and validation. Yeah, thank you.
So just 1 minute, maybe, Professor Huang, can you tell us your experience? Is it good or bad in general?
Okay, so I think
or you would like to take that another question?
I will, yeah, I will answer.
Imaging project, yeah, there's one more question.
Yeah, I will answer the first question, okay.
Sure. Thank you.
Yes, a neural network, currently I'm using the Razor-Night, shallow Razor-Night. So actually it can be viewed one of the VGG, because we know the VGG neural network is actually developed by the Oxford, so the research group. So we also use this in image processing. But we view this as a fundamental architecture. As I said, we hope not only improve the effectiveness of the system, but also the efficiency and the robustness. So we hope to build a more flexible architecture. So yeah, not only for the large data, but also for the small data site to well handle the data sparsity issue.
Thank you very much. We have more questions, but we can discuss later. So we can move forward because we have another section of April Plus, which is an additional thing that we have. So may I introduce Ihan for that? Ihan, and followed by Pratibha.
Hi everyone, it's Ihan. So as the key challenges identified by Richard, we lack of data. This is why April Plus come to the stage. So April Plus is kind of like an AI for AI hardware prototyping. So this project is managed by me and Pratibha. Actually, Pratibha is here. So she had developed the AI tool that we're also going to use, and we will see later. So by starting the April Plus projects, we will look back a little bit to what we have, our pathway to our multi-project engineering runs. And thanks to the Forte program, we established the multi-project engineering runs internally like 4 times. From year 1, the individual device level, and gradually to the array level and system level applications, and it's grown larger and larger. And for the last, normally this Forte program is happening within the collaboration universities like University of Edinburgh, Imperial College London, and also the University of Manchester. At the 4th engineering run, the last one, we decided to kind of like open this platform to all UK universities. We started a little trial on 2 of the external university projects, and it worked very well, which also brings us to thinking that maybe we want to bring this to the April Plus as well, given that we have received an additional funding from EPSRC for the April Plus. So this is the key feature for the April Plus. Well, first, we have the community-wide access to tools. So any tools that you see today, like especially in the second section, you saw people kind of introducing their digital tool and also the analog tool with the large language model feature tools. It's all open to our to the designers who participated in this engineering run. And also, with this help of AI, we're getting a higher efficiency. At the same time, the designers will keep their data set for us to help our AI to train. And at the same time, because our group also has an in-house memristor fabrication, we also offered this kind of like opportunity to the designers as a kind of like exchange of knowledge and also a way of collaboration. In this way, we built a full cycle of where you having the semiconductors and you generated data from getting the new measurement. And this data will be fed into the AI models, and this AI model will be getting improved. And later on, for the next generation of the tape-out, you will be able to boost your efficiency more and more. So here I'm highlighting several of the designers over the UK universities. For example, we have Jia Yang from University of Bristol, and also some lecturer from UCL, and also we're having the. You can also see that our projects are kind of like a wide range, from the AI processor chip, also to the neuromorphic side, and also the kind of like a hardware side. It's quite a broad topics, and it's kind of like we're trying to collect all the numerous designs that like we'll be able to get collecting data from different perspectives. Also from this this kind of like a type page, we got different universities involving in this kind of like projects. Not only from the external researchers, we also have the internal researchers from the University of Edinburgh. We're having people using both analog and digital tools to get in the similarity search at Edge, also the neuromorphic stuff. And not least, we got really plenty of research. You can see I even use like 4 slides for all the kind of like projects ranging from analog to digital. And actually, this is all kind of like for the April Plus. At the very end, I would like to kind of like bring your focus here. Please stay tuned. Because we're kind of like trying to establish this flow, and also there may be opportunities for our future engineering runs. And if you're interested in taping out with us, or join, or want to stay or keep informed on our future engineering run, please fill in this form so that we'll be able to also get you involved in the mailing list. Thank you.
Great. Thank you very much. In the interest of time, we need to move quite quickly. This was a slide about the panel discussion, but I will suggest that we'll do it later. What's more important, I think, from our perspective, is to hear our interns. So guys, can you come quickly here? Because we want to give voice to everyone, and especially I think these are the future of the AI and device design and circuit design. So it's good to hear what they think about it. So before you settle in this, the first question is, what was the best thing? I guess also the worst thing if you want. So what was the best for your experience? Go on.
Okay, I would say that my favorite part of the internship was definitely the ACID program. It was very, very new. It was a very new thing that was kind of introduced to me, where it's an outreach program where we teach elderly people how to use AI. And there were like 2 different sessions of it. And the second session, I volunteered myself to teach a little bit of explain what questions we were doing, have a little introduction phase, and question and all that with them as well. And it was a really good learning experience because we get to hear different perspectives from different ages, and they have so much to share. They just have so much to share, and the best part is that they're so willing to learn about different things, which is something very new, and I really appreciate that, and I hope to continue doing that more. Thank you.
I would say I really like April because we are such a community. We had our Dragon's Den, which is where all the interns got together to present the work that we did over the summer. There were industry professionals such as Ian Donald, who I believe is here today. It was such an eye-opening experience, especially for me, because I come from an electronics background, so I'm not really used to research, but it opened my avenues to researchers and to industry professionals, but also the interns. There's 12 of us on this internship, and working with them, doing fun Fridays, it was a really, really enjoyable experience and a great internship.
Thank you.
Hello. So it's really nice to have this platform to collaborate with other peers and to share our experience together. And I think at the end of our internship, we are also invited to UK Airs conference, and I'm very glad to see what other people are doing and listening to their experiences and knowledge, and to be able to reflect ourselves and improve our work.
And we're going to finish with this last question is to all of you guys. Did you manage to kind of communicate your research on the broader audience, like external people, not only people that don't know what you're talking about? So did you explain to your grandmas what you do actually? What did you tell your grandmas?
It's a really funny question, because having to explain what a Skyrmion is to people is a hard thing to do. Even myself, it took us a long time to read the research papers, understand it, speak to Santosh, really just speaking to him every day, asking about what a Skyrmion is and what Spintronics is and why does it make sense, what is the motivation behind all of this. But in speaking to lots of different people about it, even being here today, it's reinforcing that understanding of what we're doing. And yeah, I can say that I'm not an expert, but I understand what Spintronics is.
Someone else wants to add something?
I would just say, so I'm currently doing my dissertation right now. I'm in my final year, and me telling my supervisor what I did in my internship, it's like he himself has a PhD as well, and he was like, I was trying to explain to him in my own words as best as I could, like, what is it about? Because he hasn't heard about it as well, and but the thing is, he was able to grasp it quickly and all that stuff and catch along. But to be fair, but it was really a good experience for me to like share this aside from like Santosh as well, because like Anu mentioned, we used to talk to him like every single day about like issues we used to have. But it was overall a fun experience. But my supervisor currently right now, he's also been really supportive when I tell him about like the experiences I've learned from APO AI Hub. Yeah, thank you.
Okay, so let's thank our interns again, and thank everyone who was participating here. I think now we'll move further to the next session. All of these questions that you see here, we will try to answer, but also we can catch up, us, me, Richard, and whoever else you want to go, because we have still more things to do and job to do. So on the stage, I want to invite Atish. Atish, you're here, yeah, hopefully. And he's going to entertain us with something different.
I'll try. Hello, am I audible? Hi. So as we come to the end of this session, we wanted to walk through what are the things that April engages in, not just research, but beyond research. Let's try to just recap all the sessions we had since morning. We started in the morning with the materials design, materials discovery and device design session, which covered a wide array of topics from material exploration to device optimization and how we sort of connect the dots. The second session was about AI-based circuit design, where various approaches, various research was presented, be it for analog, digital, or radio frequency circuit design. And finally, just now, we finished the last session of machine learning. It's basically modeling for CMOS and beyond CMOS devices. I wanted to just touch back on how the research teams within the April are currently based. There are basically these 5 vertical lines, which you may have observed during today's session, starting from materials discovery, device design, circuit and system design, testing and verification, and modeling. And we're very fortunate to have a support of professors throughout the top universities in the UK. And the researchers that are currently working on these projects are sort of horizontally spread across. I mean, almost each of the researchers is involved in more than one of these teams. Besides the technical stuff that we've discussed so far, I also wanted to touch upon the ethos of April AI Hub and what we stand for. Because we are working on the field of AI, it's quite important for us to make sure that our research reflects the trustworthiness and responsibilities that AI gives the power and responsibility for us. Throughout the year, we had various workshops focusing on responsible research, sustainability of AI, and EDI workshops. We also had a fun experience with our interns. Many of them were here today and gave their experience of what they did. And we also had other outreach activities, like I guess Sarah was just mentioning about reaching out to elderly people to educate them about AI. It was a fun experience for me as well. Finally, we have everything for everyone. If you're a student, please take a look at the website. The next year's internship may be, we're still in discussion of planning the next year's internship scheme. So you might see something on the website. So far, we've had 2 rounds of seed funding projects. There are 20 ongoing projects throughout the universities in the UK. The round 3 will also be announced sooner. If you find yourself interested in having outreach activities like we done with ACID, please get in touch with our ops team member called Molly. Or if you want to have some more events that could help broaden the application of AI to electronics industry, Megan is the person to talk to. And for industry collaboration, please talk to our industry engagement officer, Katrina Netti. And finally, and most importantly, we are hiring. We are looking for researchers in all the 5 main themes that we've discussed so far, be it device design, circuit design. Please have a look on university's portal for job, and if you know someone, feel free to recommend them. Most of the information is available on the April's website, which we are also in the process of updating. So please keep an eye on that. Now, I would like to end this session with a video which is narrated by our PhD students, which discusses beyond research outreach activities that April has been engaging so far. So enjoy.
But it's not just research, right?
No, definitely not.
Yeah, we've done so many cool things. I think I personally really enjoyed the ACIT workshops where we were paired with elderly people and helped them use AI and introduce them to newer technology, and also like demystify some of the news around AI and how it can be used. I think that was really, really rewarding, and just getting that feedback from all the people who took part, saying, "Oh, now I use it to write poems to my grandchildren," or "I've been using it to write a book." That was really, really rewarding to be part of that.
Yeah, and it was very nice when we saw them taking part in our Dragon's Den event as well.
Oh yeah, that was really nice, and it was also a great chance to get an experience in making sure that we were able to present research to the wider audience, which is our duty as well as researchers.
Yeah.
That's great, yeah. I recently participated in a competition called Dance Your PhD, which is an interesting one. I recently came across with that. It's basically like you're showing you're doing PhD without saying I'm doing PhD, but just demonstrating with dancing. It's quite a fancy way. We're hopefully gonna record the video soon with a group of people from our research team, hopefully.
Who have experience from a theater play.
Exactly, like you. Well, hopefully at the end of the day, we'll be winning the prize. Yeah, stay tuned.
Perfect.
Another key point is also the game that we created, Bond or Break, which is designed to teach electronics, people who don't even have experience within electronics, all the way up to experts. A very fun, interactive game that I'm sure that everyone will have the chance to play at the annual summit. So we're really looking forward to other method of outreach to the general public.
Yeah, and hopefully we'll follow the success of the April in the Tower of Tech board book that already traveled to more than 400 schools in the UK.
Wow, that's amazing.
And yeah, we'll release more podcast episodes to give you all the updates about our outreach efforts.
Right, and that actually brings us to the close. So that, I had really the easiest kind of job today, because I've only done the intro and the end, and I mean, it's such an amazing thing, when you have all these amazing researchers and not just the researchers. I mean, you've got to sort of hear it, from them directly about all the amazing things that are happening within April. But I'd really like to acknowledge our fantastic ops team, the operations team, Anastasia, and Megan, who's been coordinating all of our different events. It's a lot of events. It's over 200 events that we're actually doing throughout the duration of April. So Megan, Katerina Netti for all the industrial engagement, Molly for all the great outreach, Aisha, who's been supporting, everything kind of acting as the glue and bringing everything together. Am I forgetting anyone, Anastasia? And yes, so there's a lot more people kind of, behind the scenes working about this. So with that, I'd like to bring this to a close. I mean, this has been, a truly challenging project to kick off, and for various reasons, but one of the best experiences for all of us. And we very much like to share this, the know-how, the tools, the people as well, because above all, it's also the people that we train through this, and the know-how that gets created throughout this. You've seen different examples where we had the opportunity of bringing DeepMind in who sponsored, like our interns, and that gave the opportunity also to our researchers to supervise them throughout this. So it's a continuous sort of development, like of people and talent, and we're really grateful to UKRI and EPSRC for making this possible. So thank you so much, everyone. I'd like to remind you all that if you could please leave your badges at the front desk. If you're attending dinner later on today, make sure that you keep the badge with you, because otherwise you will not be fed. And I would like to also ask you for the last time to use your phones, scan this QR code and actually provide us any feedback. We really want to make it better. Hopefully, I know it was an overflow of information, but we wanted to make sure that, we give you enough of all the different activities that have been happening over the past year, and still keep it all within 1 year.
Feedback form is taking you to last year's form.
Oh. Okay. So then, all right, that's part of the feedback. Thanks, Ian. We'll make sure then, because feedback is indeed very important for us to be better, and we'll make sure that we will circulate a link to all of you that is the correct link. If you have not signed up, to receive our newsletters, seriously, it's an amazing effort that has been put behind this and all the different updates. Please do spread the word about April, not just nationally, internationally, and make sure that you also attend some of the other events that we do. Today, and the annual summit is mainly about bringing the whole kind of community together, but we've been also participating in bespoke events under, like the focus of the different pillars. We will already have a date for the next summit, which will be happening in Sheffield. So please put that into your diaries from now and make sure that you follow up all the developments that April is unlocking. With that, I'd like to thank all of you for attending and hopefully give you half an hour back from your time. Thank you so much.